Starting this off by stealing a joke from Brian Regan, I think of geology as the cranberry section of the juice aisle. It's getting in all the other sciences. You looking at old bugs over there, make 'em fossils, call it paleontology. Pure physics? Well, look at this mountain, now it's geophysics. You like outer space? Let's put some rocks up there and split it 50-50. Bam! Planetary geology. The interdisciplinary nature of geology means it is vast and contains multitudes. In addition to the multiple subfields required to investigate those multitudes, the scale of geology also encompasses the history of the universe. Millions and billions of years in a concept known as deep time. Deep time is our human way of categorizing the scale of change at which geological and cosmic events occur. Earth wasn't built in a day, evolution doesn't happen overnight. Our concept of time falls short of what is needed to think about, say, the Wanapum basalts, a member of the Columbia River flood basalts. The last bits of this erupted 15.895 plus or minus 0.019 million years ago. That's a long time, and that's an uncertainty of plus or minus 19,000 years on an event that happened almost 16 million years ago. Geologically, that's state-of-the-art precision, but at a human level, what do you do with that? Think about what could happen in that time. 19,000 years ago, large portions of the land were covered in continental glaciers. Think about how much the Earth has changed in those 19,000 years, and then double it, because the uncertainty is plus or minus. So it could be 19,000 years on either side of that date. And as a geologist, you just have to say, yeah, that's our current best measurement. Here's what we think it means for the geological evolution of this portion of the continent. The farther back you go, or the less ideal material you have to calculate a date with, the worse those uncertainties become. Plus or minus a million years, or 10 or more. Time is only one dimension of geology, however. The measure of geology also includes different scales of measurement, from individual atoms to erupting volcanoes or the building of our very planet. We're going to talk about this scale starting at the level everyone is familiar with, a grain of sand. These are rocks collected during the Apollo 11 mission, part of a big soil scoop that was later sieved to remove most fines below 1 millimeter diameter or so. This sand-to-gravel fraction was termed 10085, and it tells quite a story. You see, a small percentage of those grains turned out to be made of nearly pure plagioclase. Looking at the mineral plagioclase takes us down to the macro level. We can make very thin slices of this rock and look at it at the micro level to see triple junction boundaries showing it cooled in equilibrium very slowly. Many samples have shock effects, but not all, and these plagioclase crystals grew in a large magma body slowly. The process of plagioclase accumulation to the extent to create such pure anorthosite led to the theory that the moon once had a liquid magma ocean. Essentially, it was a big ball of magma that crystallized out minerals like olivine that sink to the core, but plagioclase floats, allowing the anorthosite to accumulate as a sort of skin on the magma ocean. And this resulted in the white highlands we still see today when we look up at the moon. It has implications for how the moon formed and suggests something about how planets evolve, including our own. And all that from a grain of sand. Scientists had to apply their skills at a wide range of scales to peel back the history of these rocks. And from here we can go bigger and we can go smaller. We've already mentioned making thin sections from hand samples. We can go smaller and make microtomes of samples using focused ion beams, which can make slices only tens of nanometers thick to essentially look through these minerals in a new way. We can also measure the amounts or ratios of individual atoms that make up those mineral grains using things like mass spectrometry. I was involved in a project trying to find residue from an extinct isotope called iron-60 in meteorites, which decays to nickel-60. Individual measurements of spots in mineral grains were over 2 hours long and yielded maybe a dozen counts of nickel-60 at times. We can go finer too. If we wanted to learn, say, how those minerals grew, we might use atomic force microscopy to look at individual atoms as they align in crystal structures. And then we take all that data and swing to the other side of the scale. If we'd found the right samples with enough nickel-60, we'd be able to add another chronometer to the evolution of the early solar system, because all that initial iron-60 decayed within 10 to 15 million years ago after being formed in supernova events. And finding the right samples means thinking about how these meteorites formed and were altered over those first few million years of solar system history. It's a constant whiplash of scales that can leave the mind reeling. Now, of course, the scales don't have to extend back to the beginning of our solar system, although many do. Those rocks might seem like special cases, and yeah, they're unique, but I focused on them more because it's something I'm familiar with. That doesn't mean the same can't be said for any rock or mineral we find today. So think about the scale of geology the next time you go out rock hounding or a seemingly simple rock in the landscaping catches your eye. That agate has banding that reflects its formation conditions, and the colors tells you about what minor elements are in there coloring it, and maybe the shape reveals it was part of a basalt vug millions of years ago where groundwater seeped through. That quartzite in the river is rounded from centuries of travel downstream, stained by iron in the water, and originated deep underground in mountain building events after forming as sandstone even older than that. Think about the processes that led to the rock in your hand and what happened even longer ago. Those millions of quartz grains that later fused into quartzite were once much like the sand dunes we see today, revealing something about their environment and history. You are more than welcome to look at this rock, think it's cool, and go about your day or stuff it in your pocket. Just remember that every rock tells a story, and unraveling these stories is a matter of scale.